control, power quality, hybrid AC-DC microgrid, smart grid, solar irradiance forecasting, and renewable integration. So, I welcome Professor Pravat Kumar Rai sir to enlighten us about this topic. Please, sir.
Thank you, Pranat. So, today we'll discuss the topic power quality improvement and power flow analysis of a PV-UPQC system under a non-ideal grid and load condition. So, the contents of my presentations are, so regarding introduction, before discussing in particular to this topic, I'll introduce regarding brief idea on a microgrid. What are the different problems associated with microgrid? Out of all these problems, this power quality is one of the problem, and we'll discuss in detail regarding power quality problem. In brief regarding other problems associated with microgrid, if you will work out on this problem, how to improve performance of microgrid. And after that, in the introduction, what is power quality, what is UPQC, how to implement this UPQC, and how to implement that PV-UPQC in this system. All these things we'll cover in introduction. Next is key concern regarding operation of UPQC. What are the different problems or limitations regarding operation of UPQC? Then main contribution of this work, then the system structure or system under consideration, then regarding the control methodology. So 5 things. One is how to generate reference DC link voltage of the UPQC, which is the vital things for this one. Then regarding the estimation of frequency, we have implemented one adaptive technique that is variable leaky list mean square with notch filter based, that we'll discuss. Then regarding the generation of unit template, so we'll discuss regarding COM filter and second order harmonic oscillator CA Soho based method for this generation of unit template. Then obviously 4th and 5th are regarding the reference voltage generation for this series compensator, so that how to improve the voltage quality. And 5th one is reference current generation to improve the current quality. Then simulation result discussion, followed by experimental, how we have developed the experimental prototype, its result, conclusion, and references. So coming to a brief overview on a microgrid, here a simple microgrid we have discussed here. Only renewable we have considered is the PV. PV is the only renewable we have considered, and this PV is integrated to this grid. And now this battery and supercapacitor combined hybrid energy storage system. Battery and supercapacitor combined hybrid energy storage system is integrated to this system, and that is integrated through SST, solid state transformer. Then we have implemented here the forecasting of solar irradiance, which is the main challenging thing. And also we have implemented energy management, and regarding the electric pricing, we have implemented demand response management. So as a whole, the different things which we should take into account, or on which we have to work, are basically 5 things. Intelligent generation control based on forecasting and load management. UPQC with advanced controller to improve the power quality. Adaptive demand response management of microgrid. Advanced hybrid energy storage system with solid state transformer interface. And optimal energy generation scheduling in microgrid with uncertainty. So in brief, we'll discuss one by one. So coming to intelligent generation control based on forecasting and load management scheme. So all of us know that when we connect PV to a microgrid, the first thing comes into our mind is the intermittency nature of PV, whether we will be able to handle that issue or not. So intermittency or variable nature of solar energy will need to be addressed. Why it is required? For maintaining stability with changes in weather condition. So we can tackle that issue by means of forecasting. That forecasting of solar irradiance, if you are able to forecast solar irradiance, from that we can find out what is our PV generation. But that forecasting method is, again, we can use any model based method or image based method. Model based method means taking the data from the different weather sites, we'll model it, and using different artificial intelligence technique, we can forecast on this day, this hour, how much will be our irradiance. So that type of forecasting may not be more accurate. So for that you have to go for sky image based technique. In the sky image based technique, what we will do generally? Generally we capture the sky image with the duration, maybe in 30-second duration, one image we will capture. And from previous, just now image and previous image, we have to analyze how is the weather movement. Whether in the position of the sun, means whether the thick cloud will cover the sun or thin cloud will cover the sun or the clear sky will cover the sun. Accordingly, our irradiance will vary. So that we will find out from the cloud movement. So after knowing all these things, if this is the movement of this duration, so then after half an hour or after 1 hour, this much is the movement. At that time, weather will determine clear sky will cover the sun, then our irradiance will be more. At that time, we will determine thick cloud will cover the sun, then irradiance will be less. So like this, we can find out our solar irradiance using sky imager technique. So that is more accurate as compared to model based technique. So these are all about methods of solar irradiance forecasting. Then another thing is online intelligent generation control is to be developed, because whenever there is more load or less load, accordingly you have to store it or you have to release it like that. For that you have to develop online intelligent generation control, so that it will ramp up auxiliary sources or services in case of shortage, and will store the excess energy in case of surplus. And that excess energy will store in hybrid energy storage system. Yes. Why you have to go for hybrid energy storage system, not a single? Because when there is change in load, change in generation, then transient will occur in the system. Who will handle that transient? If you will use combined, for example, battery and supercapacitor, battery will handle that steady state part and supercapacitor will handle that transient part. By that way, we can increase the health of our storage device or say battery. That's why we have to go for hybrid energy storage system. Yes. Next is development of UPQC, Unified Power Quality Conditioner, with advanced controller to improve the power quality of pipe. In detail, we will discuss in particular to this topic. So here, now question, why to go for this power quality concept in a microgrid? Basically, when more amount of renewable are now integrated to our grid, then all the renewable energy sources are connected to grid through power electronic converter. In that way, more amount of nonlinearity enter into the system. So the power quality deteriorates. Now question, how power quality deteriorates, that we will discuss in the introduction slide, further slides. So basically, when more amount of renewable energy sources are integrated through different power electronic converter, then at that time power quality deteriorates. And that's why we are more concerned about this when so many renewable connected to a grid. And now concept is when EV is also connected to grid, then all these are connected to grid through power electronic converter, so power quality deteriorates. So that's why we have to improve our power quality. And for improvement, why to UPQC? That we'll discuss in the next slides. Next is development of adaptive demand response management for microgrid. So here the main aim of this adaptive demand response management is to bring down the cost of electricity generation by shifting the peak load to off-peak hour. So for at peak hour, let the cost is more. If you shift to off-peak hour, then our cost will be less. So for example, one of the simplest example is if you want to use your washing machine on the day, say 11 a.m. you want to use, that is your intention to use at 11 a.m. But at that time, say load means peak load is there, then you may lose your comfort or sacrifice your comfort. You may use in the night time, say 10 a.m., 10 p.m. or like that. Then by that way, you are shifting this peak load to off peak. In that way, cost also reduced. And for this also, we have to propose distributed energy scheduling algorithm to find out optimal operating time and energy consumption. So this is regarding third problem. Fourth problem is development of advanced hybrid energy storage system has with solid state transformer. So why to go for this hybrid energy? We have already discussed, because when there is sudden change in load, sudden change in demand, then at that time transients are there. If battery will handle all these transients, then health of the battery will deteriorate. So this part may be handled by some other unit, say supercapacitor, then battery will handle the steady state part. So by that way, we can increase the health of battery. And why we have to integrate this hybrid energy storage system with SST, solid state transformer? Solid state transformers are nothing but power electronics based transformer. If you use this HESS through SST, then since these are power electronic based, then there will be more flexibility in this isolation or bidirectional and charge and discharge control. That's why we have to go for SST interface. Next is regarding optimal energy generation scheduling in microgrid with uncertainty. This is important, with uncertainty. So we have discussed that so many renewables we are integrating, and in our microgrid also EV is connected. So at that time, our generation is uncertain, our load is uncertain. So if you will not consider into account this uncertainty, then whole modeling will be wrong. So that's why for randomness of demand and renewable energy generation, suitable uncertainty model is to be developed. And here also another robust estimation technique is to be developed to obtain this thing, optimal energy generation scheduling policy in microgrid. That means these are more or less 5 different problems associated with microgrid. You may work in any of the problem or more than one problem also. So if you tackle all these issues, then our performance of microgrid will be improved. So in this, we'll discuss regarding the second problem, that is development of UPQC with advanced controller to improve the power quality of microgrid. So what is power quality? So all of us know quality means it should be a good thing. So quality is a degree to which power supply approaches to ideal case of stable, uninterrupted, zero disturbance, zero distortion and disturbance free. Stable, uninterrupted, zero distortion and disturbance free. If you will get this type of power, then we can say that our power quality is good. So why power quality is now is a major issue? Because it is a critical challenge due to the widespread use of nonlinear power electronic load. So when nonlinear power electronic load are connected, then what happens? How power quality deteriorates? When our load is nonlinear, then it will draw nonlinear current from the source. When nonlinear current passes through this impedance of the line, then at the PCC, point of current common coupling, this is the voltage available become nonlinear. Since all the loads are connected at the PCC, so then power quality deteriorates. They gives non-sinusoidal voltage at the load end, leading to poor power quality. So that means when current drawn from the source is nonlinear, when it traverses the impedance of the path, then resulting in non-sinusoidal voltage at the load end. This leads to poor power quality. If power quality will be poor, then what will happen? What are the yield effects? Because so many in the distribution system, so many sensitive loads are connected. So, for example, hospitals, bank security system, air traffic control. So these are very sensitive loads. So if our power quality will be less, whatever voltage required, voltage will be less or more, then mal operation of this will occur. So that's why proper solution to the issue of power quality is the need of the solution to the issue of power quality is the need of the hour. Then how to improve power quality? So for this power quality improvement, power quality means here we are talking about both current quality and voltage quality. In the for current quality improvement, one active filter is responsible. For voltage quality improvement, another filter is responsible. So that means series active power filter is responsible for improving the voltage related qualities, voltage sag, voltage swell, voltage harmonics. Then that will be handled by this series active power filter. Similarly, shunt active power filter handle current harmonics, unbalancing in current, and regulation of DC link voltage and reactive power compensation. So if we want one only, say you are least bothered about voltage quality, let you want only current quality improvement, then better you to go for series current quality means shunt APF. So when both series and shunt active power filter are there in a system, then we call it as UPQC, Unified Power Quality Conditioner. Now we'll see the structure, how UPQC will work, how both the converters of the APF are connected. Now during voltage disturbance, for example in sag or swell, the performance of UPQC deteriorates because of absence of active power support to maintain the DC link. What does that mean? So when sag or swell is there, then support is required to maintain that sag or swell. If that extra support is not available, then its performance will deteriorate. So who will give that extra support? So for that you have to integrate PV with the UPQC. So combination of UPQC and PV with efficient control algorithm will improve the performance when sag, swell, all these things are there. Now, what are the different key concerns while discussing the operation of UPQC? Main is the estimation of frequency, why it is required, after estimation of frequency, what to do. This thing we'll discuss in the next slide. But main is the estimation of frequency and another is unit template or say phase. So if this estimation of frequency or unit template or phase become more accurate, then the reference signal generation become more accurate, then switching will be more accurate. So first is the regarding estimation of frequency or unit template. For that we have to use some algorithms. Then extraction of fundamental component from the nonlinear load current. That fundamental component is used for reference generation, so that should be also more accurate. Then active and reactive power distribution between PV load grid and UPQC with maintenance of DC link voltage or swift regulation of DC link voltage. So these are the different three concerns. One is estimation of frequency and unit template. Another is estimation of fundamental component of load current. And third is the DC voltage maintenance with management of power between PV grid load and UPQC. Now, what are the main contributions in this work? So regarding the problems or requirement we have discussed. So here we have already discussed that frequency estimation is one of the major concern. So now how we have handled this frequency estimation scheme? So here we have implemented adaptive power frequency estimation. Means whenever there is change in a load or something generation, whatever, frequency will be adapted. Adaptive power frequency estimation using variable leaky least mean square algorithm based notch filter. That is called VLLMS based notch filter. In detail we will discuss what is this filter or how we will estimate frequency for accurate and faster estimation of system frequency. Next is the normalization of positive sequence estimator. Positive sequence estimator normalization, it is required for unit template generation. For unit template generation, one of the pre-step is this positive sequence extractor. And that we have done using combination of comb filter and second order harmonic oscillator. That is N stands for normalization, CF comb filter and SO stands for second order harmonic oscillator. Using this scheme, we have to generate our unit template. So that we will discuss in detail also how you generate unit template using this scheme. Then obviously mitigation of voltage related power quality issue, that is utilizing this NCF-SO method. Then elimination of current related power quality issue. How you have eliminated? By modifying the application of notch filter. So what is the notch filter? What modification we have done for this elimination of current quality issue? Then regulation of DC link voltage, and finally power flow analysis. So these are the different main contributions of this work. Now coming to the system framework, here this is our three-phase source. Three-phase source is connected to three-phase load. This is our load, this is our source. And in between, this UPQC is connected. What is UPQC? UPQC is having two converters or two compensator. One is a parallel compensator, and series compensator. Both the compensators are connected through a DC link, and this DC link is fed from PV. This DC link is fed from PV. Now, since this parallel compensator is responsible for current quality improvement, it feeds current at the PCC. Through these filters, RF, CF, LF, all these filters. And this series compensator is responsible for voltage quality improvement. It injects voltage. For that, what is required? Transformers are required. So it injects voltage through these transformers and using different filters. So this is the basic structure. Source is there, load is there, in between UPQC is there, UPQC connected across DC link, and DC link is fed from PV. Okay, and regarding the UPQC, two converters or inverters are there, series, another parallel. One feeds the voltage or one injects the voltage through transformer, another injects the current at PCC through different filters, RF, CF, LF. This is the simple structure of an UPQC. Now, our job is how the switching of these two converters, this parallel compensator, series compensator, are to be done when there is change in load. For example, when there is voltage sag, voltage swell, then how to mitigate this voltage sag and swell. Accordingly, the switching of series compensator is to be done so that appropriate amount of voltage or current is to be injected by the series or by the parallel. That switching is to be done by different controller. For this controller, what are the requirements that we have already discussed? Estimation of frequency, unit template generation, these things are required. So now, different steps involved for the control of grid integrated PV-UPQC. So main is the first is generation of reference DC link voltage of the UPQC, that we will discuss how to generate, at what voltage you have to maintain DC link voltage. If PV is there, what is the voltage? If PV is not there, what is the voltage to be maintained in the UPQC? Now, second is estimation of power system frequency using variable leaky least mean square based notch filter. So here we'll discuss how notch filter is integrated to VLLMS, how they are combined. What is the role of notch filter? What is the role of VLLMS in the estimation of frequency? Then estimation of fundamental positive sequence unit template using normalized combo filter and second order harmonic oscillator, that in detail we'll also discuss. Then finally, reference signal generation for switching of both the converter series and parallel. These are the different steps. First is reference generation for this maintaining UPQC voltage, means DC link voltage, frequency estimation, positive sequence unit template generation, then obviously last two are switching signal generation. Then coming to first one, that is reference DC link voltage. The DC link voltage, all of us know, plays a pivotal role in the coordinated control for both the converters. Since both the converters are connected across a DC link voltage, this DC link voltage is to be maintained always, otherwise there will be mal-operation. And this DC link voltage must be always greater than the peak value of the grid voltage for the controlled switching of the inverters. Now, in our schematic we have discussed, since PV is directly connected to the DC link, no other converters are used between DC link and PV. So PV is directly connected across DC link. Therefore, it will affect the DC link voltage VDC of the UPQC. How much change in the voltage of PV output, it will affect this DC link voltage because it is directly connected, no interface. So output of VPV of the selected PV array should obligate between the minimum and maximum. This PV output should remain, we have said, should remain within 600 to 800. This minimum and maximum value depends on this grid voltage and also rated voltage of the considered DC capacitor. Based on the grid voltage and rated voltage of the DC capacitor, we have to fix minimum and maximum value of DC link. Now, for this one selected reference DC link, VDC reference is decided by this P and O algorithm. When PV is there, VDC reference is to be selected by P and O algorithm. But when PV is not there or non-SPV hour, then DC link voltage is DC reference is to be set by this equation, where this V line to line norm is the V line to line voltage √2 by √3 into 2. So in this way, when PV is not there, you have to set this. When PV is there, you have to set a VDC reference between 600 to 800. These are regarding generation of reference DC link voltage step, first step. Then second step is estimation of system frequency. So for system frequency estimation, we have discussed that we have to use that VLLM, that is variable leaky least mean square based notch filter. So here power signal frequency is estimated by using second order IIR notch filter. So its transfer function is this one. Second order IIR notch filter transfer function is this one. This is the transfer function of second. This is the transfer function of this second order IIR notch filter, where from this we will find out what is error, EZ. This EZ is to be minimized using any signal processing technique or say soft computing technique, but here we have used that variable leaky least mean square based algorithm. So we will discuss now how this error will be minimized. When error will be minimized, then our estimation of frequency will be more accurate. That is the objective of any method. So here, to make the operation suitable for practical application, this filter is considered in the discrete Z domain. In Z domain it is mentioned. Here omega 0 is the notch frequency which is to be adapted such that it lies between this range, and R is the pole radius that determines notch width. So we'll see in the border diagram how based on R value the notch width will vary. So now our objective is to minimize this E using variable leaky least mean square based algorithm. So whatever we have discussed in the previous slide, that is this one. So if you will solve this one, you will get one E expression in terms of S. This will be cross multiplies and you will get one E expression. That E expression is this one. So this, whatever this equation is implemented here. This equation is implemented here. What are the inputs? The inputs is the VSABC. SN is the input, which is our grid voltage, VSABC. So whatever error is fed, this error is fed to variable leaky LMS based estimation. This estimation, before this estimation of this leakage factor, step size, autocorrelation matrix is required. For this estimation or updating, error is required and input is required. And for final updating of omega 0, also error is required, input is required, and output from this are also required. So taking all these input, so will determine this omega 0 head. Omega 0 head means that frequency. So how to determine this omega 0 frequency? So how to determine? These are the steps. These are the steps. So here these steps are: one is for updating of leakage factor, one is for updating of step size, another is for updating of autocorrelation matrix. So in detail is there in one of the references published in IET, that is variable leaky least mean square based power system frequency estimation. So for this analysis, these are the different constants used. So you have used different value for these constants, and using all these steps means here the finally the input is VSABC, that is fed to this notch filter. Error is generated based on this equation. This error is to be minimized, and for this minimization we have used this variable leaky least mean square estimation for updating this omega 0. And for updating omega 0, we want updating of these three equations. And for updating these three, also you want error input and this VS input. So after updating all these three, we finally updated omega 0. This final updated omega 0 is used in the further steps. Yes, but PLL based frequency, it will be sluggish in the system, slow response. So one comparison also we have shown in the paper, one of the paper, this is actually under review. So PLL based, here also some slides are there, PLL based technique, non-PLL based technique. What is the performance? That also I will show, some slides are there. So some technique we have used where PLL is used, and this technique where PLL not used. Comparison is also there. Okay, no issue. Yeah. Moving average also you use, but here the notch filter, the rejection is means filtering capacity. This notch filter is basically a band stop type of filter. Rejection is more, means I will show the border diagram how it rejects all other frequency except fundamental frequency. I will show in the border diagram is there. Okay. So here estimation of fundamental unit template using NCF Soho method. So here in the grid integrated mode, prompt and accurate generation of pollution free, balanced and grid synchronized unit templates is required. So for generation, basically this scheme is for generation of unit template. And after generating unit template, what to do also we'll see in the control structure. Why unit template is required. And that unit template should be perfect, more accurate. And for that we have used this normalize CFSO. What is CFSO? Why normalization required? That also we'll discuss. So first step is, this is our grid voltage or source voltage, that is VA, VB, VC, or say VSA, SB, SC. That using Clark's transformation we will convert it into V alpha, VB. This is simple one. So we have converted ABC to alpha beta static frame. Now this alpha beta, whatever we have obtained, that is uncompensated orthogonal component, V alpha, V beta. If we use this component using our template generation, then while there is voltage sag or swell, then there will be problem. So it will not give means accurate result. What type of problem will be there using this one? That also we'll see in the results. So that's why what we have done, processing of this V alpha beta is required. And this V alpha beta signal are further processed by using CFSO. What is CFSO? That also we'll discuss. So that means here we'll discuss first step is VABC converted into alpha beta. And whatever V alpha beta is obtained, that is unprocessed. If you use that V alpha beta for template generation, then accurate result will not get. That's why some processing of V alpha beta is required. So here that processing is to be done by CF SOHO, combo filter, COM filter and SOHO, second order harmonic oscillator. So what is COM filter? COM filter is basically this is the transfer function of COM filter with the time delay TD, and transfer function is just 1 minus e to the power minus STD. So that means if you feed input to this COM filter, means V alpha beta you feed this one, then you will get a time delay signal. And this delay signal is to be subtracted from this V alpha beta. That is V alpha beta CF, COM filter output. So just here what you have done, signal fed to a COM filter, output obtained is COM filter based V alpha beta, where delayed signal is subtracted from the original signal. This step. Now second step, the output obtained from CF, this one V alpha CF beta CF, or otherwise say V alpha beta CF, is utilized to control and trigger the operation of the second order harmonic oscillator or SOHO. What is SOHO? What will operate? That will see. So basically, the second order harmonic structure means oscillator source structure is like this. So V alpha beta, whatever you obtained previously, that is used here, and here we will get this alpha beta plus positive sequence estimator, its derivative V alpha beta plus dot means derivative. So now, if you will use or convert it to S domain, convert this signal into S domain and find out V alpha beta plus S by V alpha beta COM filter. Means COM filter given as input and output is positive sequence obtained, alpha beta plus. Then transfer function become output by input. This output by input will obtain this one, which is nothing but gamma by 2 into S minus j omega. From this, if you convert into S domain, you will get this equation. Right. So now what we obtain? We obtain the transfer function of SOHO. SOHO means second order harmonic oscillator, whose output is positive sequence component alpha beta plus and input is the output of COM filter. Now, then finally, now by considering both CF and CO, what is our objective? Our objective is both CF and SOHO. So SOHO. So here SOHO transfer function we already obtained this one, that is V alpha beta plus by this one equal to gamma by this one. SOHO transfer function is V alpha beta plus by V alpha beta compensated. We obtained this as CF obtained as gamma by 2 into S minus j omega 0. Now we multiplied both this. This is a SOHO output. CF output you have to multiply. What is the output of CF? Output of CF is V alpha beta CF and input is just V alpha beta. So V alpha beta S by V alpha beta S. So now this V alpha beta CF get cancelled. So what will obtain? Alpha beta plus by V alpha beta, and here you have to multiply its transfer function. What is its transfer function? 1 minus S. Its transfer function is here 1 minus e to the power s td. So now this 1 minus e to the power s td multiplied with this one. This is obtained overall transfer function. So now our objective is to get unit magnitude response at fundamental frequency. So that means our magnitude will be unit. So magnitude, how to find out magnitude? Magnitude of this one. So put s equal to j omega, take absolute value. If you take square of this one, you will get this expression. So this is equal to, since we have this magnitude should be 1 and we have taken square, it should be 1 square. But now our aim is to determine at what omega, at what gamma. Gamma is the speed. At what gamma value to find out. Determination of gamma for omega tends to omega 0. If we'll, for this equation, if you will take limit omega tends to omega 0, then this become an indeterminate term. So that indeterminate term in mathematics how to solve? Using L-Hospital rule. So if you use L-Hospital rule and you will solve this one, you will get this gamma equal to omega 0 by 2 pi. So that means above consideration of unit magnitude at omega 0 during any disturbance in the grid with respect to magnitude, the magnitude response will not be that. What is the meaning? Our aim is at this fundamental frequency, our response will be unity. But when This is for when there is no disturbance in the signal. But when there is disturbance, for example, sag is there, swell is there, at that time our magnitude will not be unity. So that's why magnitude will be either greater than or less than 1, depending on whether swell condition or sag condition. If no sag swell, then it's perfectly 1. But when there is sag swell, it will deviate from 1. Then how to tackle that issue? To tackle that issue, you have to go for normalization. So that's why CF-SOHO estimator is modified by introducing a normalization factor, sigma normal, into the output of CF-SOHO, so that it will lie in the unit only. Regarding the result, we will see how using normalization we obtain unity. Before normalization, what is the result? After normalization, what is the result? Now, for improvisation and practical implementation, the CF-SOHO acceptor is discretized, and the CF transfer function what we have discussed earlier in Z domain, this is the structure 1 minus Z, that means delay of TD, and this V alpha beta NTS equals to whatever V alpha beta minus its delayed version this CF output. CF output is what? Signal minus its delayed version. In Z, this is the signal, this is its delayed version. And whatever discussed this 9 equation, this equation is modified using some mathematics, that invariance methods. So modified to get this equation. So the difference equation of SOHO as discussed in 9 is given in 16. Now the output V alpha beta 1 plus become these two components. One is this component, another is this component. These are implemented here. Say whatever discussed V alpha beta given to COM filter, output is V alpha beta CF, COM filter output. Now this fed here, this is the matrix, so we'll get this equation here multiplied, right? Whatever obtained, its delayed version, initially this component is 0. So when the second term will come, so now this Z inverse is multiplied with this one. When Z inverse multiplied with this one, delayed version, if since this is TSN plus 1, its before version is NTS. So this second component will come because of this one. So finally we'll get V alpha beta 1 plus. Okay, so now this V alpha beta 1 plus is used for this its analysis. We have seen here. So we have already discussed normalization is implemented. How to do normalization? Just magnitude square root, we have to multiply normalization, any normalization technique, simple. Sigma normalization alpha beta equal to V alpha 1 square, V beta 1 square root over. So this thing implemented here. In the previous slide, see these things are not there, this thing is not there. So whatever V alpha beta 1 plus we have taken. Here we have given this normalization to tackle the issue of this voltage disturbances. So this normalization now fed. So here what happened, after all this processing, again delay comes. This V alpha beta 2 plus is delayed by half cycle maybe. To compensate delay, this rotation matrix is multiplied. And finally we'll get V alpha beta plus positive sequence component. This V alpha beta plus means alpha beta converted to ABC. Now we'll find out UI, UIB, UIC. So V alpha beta plus is transformed into ABC frame to get 3 unit templates. So these unit templates are used in the subsequent control. In the how these are used, we'll see now. So whatever discussed till now is estimation of frequency, estimation of this positive sequence component. So now this step is how to generate switching for both the inverter. First we'll discuss for this one SEC means series compensator. We have used two compensator, one is series, another is short. This is used for injection of for series compensator. Switching signal, how to generate switching signal for this series compensator. Series compensator is responsible for what? For improvement of voltage quality. So now whatever we have discussed, VS ABC signal converted ABC to alpha beta. This to notch filter, adaptive notch filter when fed will get omega 0, this frequency, omega 0 frequency. And here we have implemented adaptive means variable leaky list mean square, notch filter implemented already to obtain this omega 0. Now here VS ABC to alpha beta, this here we have implemented NCF SOHO means normalized comb filter second order harmonic oscillator. So means its output, what we obtain, its output are unit template. We have already discussed how obtained. These are the three signal UIA, UIB, UIC obtained. Okay, so now up to this we have discussed, up to this, these three signal we have generated previously. Using this signal, what to do here? See, another is whatever V line to line normal multiplied with 2 by root 3. This multiplied with UIA, this multiplied with UIB, this multiplied with UIC to find out VLA, LB, LC. These are the equations. VLA reference, this voltage multiplied with unit template. This voltage multiplied with unit template B, similarly unit template C. So in this way you obtain VLA reference, LB reference, LC reference. These are the load voltage references generated using control algorithm. These are to be compared with the actual source voltage SA, SB, SC. When you compare, you generate the signal difference. This difference is the series injected reference voltage. For injecting the voltage, one reference is required. So that reference and actual series injected, they are compared, fed to the hysteresis current controller for switching signal generation. This is the principle. So here overall, first we have estimated frequency using adaptive notch filter. Then we have estimated using NCF SOHO, that unit template. Then from the VLL, V line to line, we'll find out voltages. That voltage multiplied with references to generate VLA, LB, LC reference. These references compared with source voltages to generate injection signal reference. These injection signal, these are the reference compared with the actual signal, error whatever obtained, fed to hysteresis current controller for switching signal generation. In this way, switching signal pulses given to series compensator. These are the scheme for one part, that is series compensator. Another is shunt part or parallel compensator. So here, for parallel compensator, reference signal generation for parallel converter, here three things are there. First is fundamental active current component of load current by using notch filter. Fundamental active current component generation by using notch filter, one thing. Second is switching loss component, compensating component by regulation of DC link, that is second thing. Third is contribution of PV towards load and grid, third thing. In detail, we'll discuss one by one all these three. So first is regarding fundamental active current component generation, that is IFL-ABC, fundamental active current component reference generation. Second is switching loss compensating, that is IDC. This is second. Third is contribution of PV. Since PV is connected to the DC link, what is the contribution? That is IFPV. So how all these, then taking all these three, we have generated switching. In detail, we will discuss how generated. So coming to first one, regarding fundamental active current component of load current by using notch filter. So what we have done? Here, basically, whatever load current is there, if it is fed to a notch filter, then what happens? This error generated is, except fundamental, it will give all the signal. Means this signal contains second order, this IAE filter. This signal contains what? Except fundamental, all are there. Now, if you subtract this signal from the original, then what will obtain? Fundamental only. So in this way, we obtain IFL ABC. This is implemented in the previous slide. So now, this is the figure showing the border diagram of this notch filter. Means here, what happened from this figure, at fundamental frequency 314 radian per second, the magnitude of response is unity. See, here, this is 100, so 314 will be somewhere here. So at 314 radian per second, the magnitude is unity. How to check unity? If you draw this one, it will come here. Magnitude unity means log 1 will become 0. So that's why here it touches 0 dB. So that means at fundamental frequency, the magnitude is unity. We have discussed already at fundamental frequency, we have taken that one. So this is confirmed. And at a non-fundamental frequency, the magnitude is negative, which shows that signals are fully attenuated. Non-fundamental frequency means this radian, this value, 2 pi f value will not be 314. It will be some other value here, this side, this side. So here, see, these are coming to negative. That means it rejects or attenuates signal. That is our objective. We'll take only fundamental, rejects all the signal. And also at the DC offset is also removed. DC offset means 0, frequency 0, 0, or here we have taken 10 to the power 0 means 1, 1 is close to 0. So at 10 to the power 0, see it is also negative. So that means this notch filter rejects all the DC offsets, all the different frequency other than fundamental. That is confirmed from this border diagram. Now, we are continuing regarding this generation of this switching pulse generation for this parallel converter. So first we have already covered that generation of this fundamental component of load current from the modified notch filter. So this omega 0 fed to notch filter, whatever obtained, that is except omega 0 frequency, all the signal that is to be subtracted from ILABC to get fundamental. This thing we already discussed. Now, taking this fundamental component also contains what? Reactive component of load current. It also, fundamental component obtained still contains some reactive component of load current. But our objective is to remove reactive component of load current so that we will get a good unit template. Finally we'll get good unit template. So for that, how to remove this reactive component? For that we have used this technique. What is this? That we'll discuss. For reactive component is separated from this ILABC using quadrature unit template. Quadrature unit template is what? In phase unit template generation we have already discussed UIABC. We have already discussed UIABC. UI stands for in phase unit template. From in phase unit template, quadrature unit template UQABC will using UIABIC like this. Using all these UIABC, we can find out quadrature component. Okay, because we know in phase component from UIABC means we know UIA, UIB, and UIC. From this, knowing this value, you can find out UQA, UQB, and UQC. These are the quadrature component. Okay, so knowing this value, you can find out this value. Clear? So now, this quadrature template is fed to the zero crossing detector. See, these are the ILABC, UQA, UQB, these quadrature component UQA, QB, QC fed to ZCD, zero crossing detector. What it will do? To determine the instant when the quadrature component magnitude goes to 0. Zero crossing detector means at what instant this goes to 0. That instant you fed the signal. So at that particular instant, the value of ILABC is processed. When it will go to 0, at that instant it is processed till next zero crossing of quadrature unit template obtained. So in that way, that means UQA through ZSD find out the instant. At that instant, you process sample hold circuit. Then whatever you will get, that absolute value you take. Similarly, for this case also, absolute value take, absolute value take. Then take the average. So average magnitude of active load current become IF average equals to IFPA PB PC by 3. So in this way, we will find out this IF average, that is one component. We have already found out this one step, this one, second step, this one. So next is regarding switching loss component and PV feed forward component. What is PV feed forward? What is switching loss? See, while compensating harmonics and reactive power demand of the load, certain amount of switching loss occurs. While compensating harmonic compensation, while we'll use in the control algorithm, while compensating harmonic and reactive power, some switching losses are there. Then who will provide that switching loss? That switching loss first instant will be provided from the DC link. Then DC link is to be maintained. Otherwise, there will be mal-operation, system will not work. You're getting? For compensating harmonic or any other disturbance, switching losses occur. Who will provide? Suddenly that switching loss will be provided from DC link. Then DC link is to be compensated. So how much DC link required? That is IDC. Means how much current required to compensate the loss, switching loss. That is IDC. So for proper operation of UPQC, regulation of DC link voltage, a desired frequency is crucial. That is to be found out, and for that we have used a PI controller. So whatever IDC initially through PI will process, will find out this IDC. So for that you have to find out what is our error, what is VDC reference. If VDC will now go down, then difference error will find out. Are you getting? For example, our VDC is say at 700 or 705. 705 is a VDC. When sag or swell occurs, we are operating our control algorithm. At that time, some switching loss occur. Now, to compensate switching loss, it draw from DC link. Now, DC link voltage drops. So, error will obtain some value reference, now drop. So, for that error, to maintain that one, how much it will draw? That is IDC. So, these things are implemented here from PV, P and O, VDC reference set. When no PV, that is 680, we have calculated. We have given 2 root 2 by root 3, that one from that expression, 680. So in this way, we will get VDC reference. So actual VDC passes through PI controller, we will get this IDC. Then this is regarding first part, switching loss component. Second part, PV feed forward component. What is that one? We have already discussed in the schematic. PV is connected directly across DC link. In the schematic we have given PV is connected. When PV is connected, some current it will provide through PV. Now, PV is connected in the DC side. DC side, its AC equivalent current, how much PV is providing, its AC equivalent, that is called feed forward. If PV is not there, then some more current will draw from the grid. But PV support is there. That much amount of current we are not drawing from the PV. So that's why we have to make it minus. In the subsequent slide we'll see. So it is the AC equivalent of PV current at the AC side of UPQC, and it is using, this is IF PV. From this you will find out this equation. This is just a 3 VI cos phi formula. This is V, this is I, VI cos phi formula. So we obtained IFPV. So that means this IFPV is the AC equivalent of PV current we are feeding. Right. Now, we obtained already three things. IF average divided by 3 we obtained, na? IF average, this one. IF average. Then obtained IDC and IFPV. Why IFPV is minus? Because PV is providing. If it is not there, we will draw more current from grid. So that's why this is minus. So in this we will find out IS reference. This is a value. But to get the signal, you have to, it's to be multiplied with a template. These are the template. So UIA, IB, IC, these are the template. How generated? We have already discussed. These template multiplied with this IF reference. When A multiplied, ISA, B multiplied like this. So these things, so now ISA reference obtained, SB reference, SC reference obtained. So these are the, whatever you have discussed, these are implemented, and this is ISA reference, SB reference, SC reference. These references compared with actual. These are the actual ISA, SB, SC. They are error fed to hysteresis current controller for switching signal generation. So these are the schemes. This is the scheme for parallel compensator. And we have already discussed for series compensator. So these two are implemented. So this is system for the simulation implementation, sibling implementation, system parameter for simulation study given, taken like this, different values. Now, regarding the results. So here, first one is system dynamics under grid voltage sag and nonlinear load at constant solar irradiance of 500 watt per meter square. Load is nonlinear and voltage having sag. Two problems are there. Voltage side problem is there, current side problem is there because load is nonlinear. So you have to handle two issues. One is voltage sag issue you have to handle, current harmonic issue you have to handle. So for that, whatever signal is there, say sag is created from here only. At t equal to 0.2 second, grid voltage sag of 30% is created. So before 0.2, same actual voltage, no sag. And at 0.2, sag is created. Now, this is the V alpha beta converted V ABC to alpha beta. Then COM filter output is what? When the system is steady state, COM filter give 0. No disturbance, it will give 0. When disturbance is there, it will give some signal. See, disturbance is here, so it will give some signal. After some time, this same thing will continue, so that's why 0. So this is the output of COM filter. Now this COM filter fed to SOHO, second order harmonic oscillator, to find out V alpha beta 1 plus positive value. So now it obtained, but only thing is, in the output you see, sag is also visible, noticeable. This voltage sag is there. It is not same as to that of this. And it is not in the unit, means minus 52 plus 50 is there, not in the unit. Then we have to go for what? Normalization. We have already discussed how to normalize. So after normalization, this is the result where sag is not there and it is in the unit. So these are the output finally of this CF SOHO. Means this much, this is the unit, positive sequence, this generated signal. These are used for that unit template generation. Then these are used for unit template generation. Then finally switching occurs using our control algorithm. Then switching occurs here. These are the signal given, means VL, these are the series injected signal. Then now this becomes sag become eliminated. But since at 0.2 sag occur, that's why this line is this one reference. So in this way, this is the regarding working of series compensator, because series compensator is responsible for sag swell elimination. Then here in our problem, two things are there. Sag is there and nonlinearity also there. That means our parallel converter or compensator will also work. See, these are the results. Since this is a nonlinear load is also there, our load current is nonlinear like this. And using our whatever control algorithm, we have done the switching. So these are the compensating signal given at the PCC. Now this is the IS ABC. And this is regarding DC-link voltage is maintained. First sag is created here. Though sag is created, little bit oscillating, but it settles. See 0.2 oscillation start, 0.25 almost settle. Within 0.05 second almost settle, DC-link voltage. And these are the TSD, 26.16 before compensation, 3.34 after compensation for the load current. Now, we have also discussed regarding power balance between PV, grid, load, power balance is there, is to maintain. This is the case. With irradiance of 500 watt per meter square, P load is P grid plus P PV. See, Load active power is more and PV power is here, PV power is less, grid power is also less. In this case, both PV and grid will support load. But at point 2, sag occurs in our question or problem, sag occurs. So when sag occurs, then what will happen? ACC means series compensator active power. Before sag, 0, no given, nothing given. But when sag occurs, it will provide. So when it will provide, then since PAC is responsible for maintaining the voltage, PAC will be little bit downward. So these are the results for reactive power management. Then regarding reactive power distribution, load reactive power is to be maintained by PAC, that is load reactive power and PAC reactive power maintained, and grid reactive power and SCC series compensator become 0. So that means in phase compensation of sag occur. So in this result we obtain that sag is compensated, that nonlinearity is compensated, DC-link voltage is maintained, power balance maintained. Power balance means both for active power and reactive power. This is the same
Can
whatever
I
you
ask a
discuss for
question?
sag, this is the case for swell. The voltage
Hello.
increases. So at point 2, any question or what?
Yes, sir.
At
Sir,
point 2,
can I ask question?
yes.
Sir, how you have introduced this voltage sag and everything in MATLAB software? I think this have all been done in MATLAB.
Yeah, MATLAB and also in the experimental also we have verified intentionally we have created sag.
So how you have means how can we create this sag in software, MATLAB software, sir?
Through Simulink giving programming means that at that value, at that instant, our voltage will be reduced to this much. 30% we have reduced.
In the Simulink, in
Yeah,
Simulink, sir.
yeah. We have reduced that much amount, 30%, maybe 20%, 40% like that. And whatever you have generated, that we will have implemented using DSpace or microlab box in the hardware experimentation.
Okay.
So here we have tested 30% and maximum 40% or something tested for this sexual, not beyond that.
Okay, sir.
Thank you. Have you? That code something. So that we have not considered in the laboratory. We have we have only considered 30%, 40%. What is their code? How much possible that we have not taken into account. Okay. So whatever you discuss for say case, this is same thing for swell case. Here point 2 swell occurs. These are the output of alpha beta CF. Then this is alpha beta 1 where this swell is also visible. Then finally alpha beta plus, that is after normalization. Then from this signal we have generated our unit template, and accordingly we have generated our switching pulses. These are the switching pulses. These are the compensating signal fed through series compensator, and finally we obtain sinusoidal signal. This is regarding voltage. Then regarding current, here also nonlinearity is there. So current is non-sinusoidal, load current. Now these are the injected signal and these are the current become sinusoidal. And regarding DC-link voltage, whatever we have discussed previously, same thing maintain. TSG 26.16 before compensation and after compensation 4.78. And these are the regarding reactive power and active power distribution, just like we have discussed. At point 2, swell occurs. So when swell occurs, then series compensator in this case will take some power. So that's why this is just like this. And these are the corresponding other curves. And here also P load power is maintained by grid and PV. And this is regarding reactive power compensation, just like sag case. This is the case when system dynamics with harmonics in both grid and load. Harmonics is there in grid and also in load. That means voltage having harmonics, current having harmonics. See here, at 0.2 second, harmonics of 5th and 7th order are imposed on the grid voltage. Then what will happen? See, up to this, no harmonics. So that's why 0. at this instant changes. So that's why it is showing. Then after that, same thing continue. So 0. Then this is alpha beta 1 plus. This is providing this one, but not within unit. So that's why normalized. This is the normalized output. Taking this, we have generated this pulses. You IA, IB, IC, then further thing. So now this is our VS ABC at point 2. This is distorted. Now this is the signal injected. This is the final. Here this whatever we have discussed, this 18.24, that is voltage case TSD before compensation, 1.18 after compensation. Now coming to current case. This problem, voltage is harmonic, current is also harmonics. So the load current is highly distorted like this. These are the compensating current fed by parallel compensator. These are the sinusoidal obtained. And here also DC link voltage is maintained very accurate, means within this thing, means 0.2 to 0.3 it is maintained. And this is just like active power distribution, reactive power distribution, whatever discussed for Seg-Swell. Here also, both for grid and load disturbances, these are the results. Then coming to power system dynamics under varying PV power generation. Here we will see PV power is sufficient, PV power is balanced, PV power is deficient. So in that case, how this work? See, over this period, this to this one, that is from t equal to 0 to 0.18. 0.18, 0 to 0.18 somewhere here. So here you've taken PV is operating sufficient power mode, means PV is more. PV is more means whatever load demand, it will take from PV and rest grid will take. So that's why here grid will take, see, since grid is taking, this line is starting from here. This line, blue is here, since grid is taking, that's why in the down. Grid is taking over this part. And this PV is feeding power here, that's why PAC is this one up to this. And after this, in this portion, what happens? PV power just balanced. PV and load are same. So PV is directly means giving whatever amount load PV is giving. So from the grid, no power. And here what happened? PV power is less than load. So when PV power is less than load, then both will support PV and grid. So that's why this is PV support, grid support. And here in this portion, PV power is 0, no PV power. So when no PV power, then grid will support. So these are the different results. Then in this situation also, this is the situation showing when PV is there, when no PV is there. We have discussed when PV is there, our reference we have said 600 to 800, it will lie somewhere here, 600 to 8. When PV is not there, we have fixed at 680. So it is below this one. And here, this active power distribution, when PV power is greater than P load, equal to all these 4 cases, whatever discussed, these things are shown here, power management. Now, this is a comparative study showing frequency estimation and positive sequence, what you have asked these things. Means here, performance of VL, LMS, ANF, adaptive notch filter, and NCF SOHO with below existing technique. So here we have taken PLL, SRA PLL. This is CDSC PLL, cascaded delay signal cancellation based. This is dual second order discrete, means D SOGI PLL. And this is a linear Kalman filter based, no PLL here. So no PLL is one is there. And these are all PLL. And our is also no PLL. So comparison done for all these cases, different cases taken are grid voltage imposed with 5th and 7th harmonic, with frequency jump also 5 hertz. And second is grid voltage with phase jump. And third is regarding grid voltage imposed with harmonics of 5th and 7th. See, here comparative analysis of proposed frequency estimate of the existing method. See, here different methods with different color given. So estimated frequency during the period of grid voltage harmonics, this thing zoomed version here. This yellow one are the SRA PLL. So here it is seen that using SRA PLL method, effect of harmonics noticeable on estimated frequency. Means it is exactly showing other estimation technique, no PLL method. SRF PLL with PLL, this is showing some content of harmonic is showing in the even if frequency estimation. And regarding jump, say here plus 5 hours jump is there. So plus 5 hour zoomed version. See, all other methods are showing this one, and this VLLMS, see this overshot is not there. So this is the comparison. So what happens due to PLL less operation of VLLMS ANF, the frequency curve is smooth and swift adapts to changes. VLLS, this method, the frequency curve is smooth. But other technique involving PLL introduce a delay due to transformation of signal from ABC to DQ. In the PLL method, that DQ transformation is there, rotation frame. Because of that, delay occurs. That's why so many things are there. So this is just a comparison, and it is showing that PLL less method. So that means VLLMS, ANF better result as compared to this one. Even if this is LKF method, this is PLLS method, PLL less method. It is showing good result also. Regarding this estimation, it is showing good result. But here, this frequency settling time is more here, and this is less here. This is the case for grid voltage with phase jump of 50 degree taken. See the signal, now suddenly phase jump 50 degree. All other estimation techniques showing this jump, but here, see these PLL-less methods are not showing jump. Even if phase jump is there, no problem in the estimation of frequency. These are the comparative statements. And these are the comparison of regarding this generation of this positive sequence extractor. So here we have used compare our method CF SOHO comparison with other methods CDSC and DSOGI and unprocessed signal. This is unprocessed signal. When you convert it into orthogonal signal, even if see this nonlinearity is there. Here unbalanced is there, nonlinearity some it is not sinusoidal. Here some amount nonlinearity is also there. Here pure sinusoidal we are getting this one. And also this portion settling time here and here started from initially. Now coming to this is the development of prototype in the laboratory. So whatever you have discussed, these control techniques are implemented in micro lab box, and all other sensor boards are there. Two UPQC having two converters. Series injection transformer are there for injecting this voltage signal, and three-phase rectifier is there, load box, three-phase variac, DSO. All these are the total prototype we have developed in the laboratory. These are the different parameters taken. So these are the results, hardware results. So here we see that performance under nonlinear load condition, three-phase nonlinear load we have taken this one. So here it depicts the undisturbed grid voltage. See, only we have taken nonlinear load. Grid voltage is good, means no disturbance. So grid voltage is good, VSA, SBSC, and LALB. Since in our DSO only 4 channels are there, we are not able to show this. This is the LA we have shown. LB, LC we are not able to show here. That's why we are showing here. So VSA, SBSC, this VL, LVLC, no disturbance here. But here, this one is the no rejection, no voltage injection by SCC. These are the voltage injection. Since voltage is maintained, no disturbance, so no injection. That's why it is maintained, no disturbance. But now we'll see regarding the current case. Current case, since current is nonlinear, load current is nonlinear, we have to inject something to make it sinusoidal. So these are the injections. PACA, parallel converter. PACA means parallel converter. A stands for A phase. A phase, B phase, and this is C phase. These are the different injections. So when there is change in voltage, then tracking of VDC is also maintained from 0 to 200 volt. And these are the grid current is maintained in this way sinusoidal, and this is the load current highly distorted. Load current is highly distorted from sinusoidal, and grid current is now sinusoidal after injecting this compensating signal. And these are the different THD value of load current, grid current, all this. This is regarding SEG case, whatever you have discussed for simulation, this thing we have experimentally verified. SEG is created, 25% SEG is created here. See, this VSA seg is created here and actual will be at this level, seg is at this level. Similarly, VSB, SB, seg is at this level, actual is at this level. And these are the zoomed version here you taken. And this is regarding VSC. Actual is this level, seg is this level. So that means seg created 25%. And so increase in series injection voltage of phase A and B due to compensation of seg. See here seg is created. That's why these are the injection voltage. VACA means series injected voltage at A phase.